Learning about spanning tree protocol can be a challenge. So in this video, I'm going to take a more human approach rather than focusing on the intricacies of what the switches do. However, you still need to learn a lot about STP before you can get a great idea of the big picture. So be patient while we get through this fairly long video. So this video tracks to the content in the Volume 1 Official Cert Guide, in particular Volume 1, Part 3, Chapter 9. That's Chapter 9 in both the old Edition 1 and the new Edition 2 that came out in 2024. And in that chapter, in the Edition 2, you'll see 4 headings that you see on the left. By the way, the 4th heading at the bottom there, that's a new 4th major heading versus the Edition 1 book. Anyway, we're focused on that first heading, STP and RSTP Basics, Spanning Tree Protocol and Rapid Spanning Tree Protocol Basics. So I've taken that material, but I'm taking a much different view of the material here in this video than in the book. The book focuses on how switches achieve spanning tree. And here I'm taking a more simplistic view to show you how humans can think about it and get the same answer while ignoring some of the protocol details. To do that, I've organized this video into 5 sections. So the first section talks about redundant physical topologies, which are great. And that's what people build because things break, and then we'll have redundant links and devices to use when that happens. But what we're driving toward is in the last topic, which is a loop-free, non-redundant spanning tree protocol topology that's in use right now, and then if something fails, then we can change it to use the redundancy. The process is the middle 3 steps, the components. So you've got to get all 3 of those pieces of the process down before it makes sense of the outcome, which is the loop-free spanning tree topology. All right, so that's the context for the video. As always, I make a few promises. Stay till the end. I know, I told you it's a long video, but at the end, when I close, I'll tell you what to make use of in the book. That's more important in this video than most any of them, so watch for that. Also, I'll give you some review activities at the end. And then finally, I always make an extra promise here. This video is about spanning tree protocol and rapid spanning tree protocol features that are in common. I'll give you a few quick words about things to look forward to when you start getting into the rapid spanning tree protocol details. Let's begin by looking at a fairly typical campus LAN design with a couple of distribution switches that connect only to access switches and access switches that connect to end user devices. Those links between switches are often VLAN trunks to support multiple VLANs. Then the access switches connect to end user devices, and they're often connected to multiple different VLANs, which is what drove the need for the VLAN trunks between switches in the first place. We've talked about that in an earlier video even. So what do we do about that in regards to redundancy? And you might even think, well, what's the big deal? So let's talk about what the big deal is, right? So I'm going to use this simplistic design. This is not something you go deploy necessarily, but it gives us a nice backdrop to talk about the issue. It's just 4 switches with redundancy, right? There's 2 paths between each of those 4 endpoints, right? You can go clockwise and counterclockwise, if you will. So the issue comes in that switches like to flood frames by sending frames out all other ports. Now, I'm going to use this example throughout the video. So just to hit the interface numbers, I use a consistent interface numbering scheme. The last digit is 1 on all the ports connected to the endpoints. And then all the ports that connect over to switch 2 end in 22. The interface on the other end of the link. All the ports that connect over to switch 3 on the other end of the link, the interface ID ends in 23. All the interfaces on the other end that end in 4 connect over to switch 4, and you guessed it, to connect to switch 1, the other end of the link, the interface IDs end in 1. Now, why do I tell you this? We're going to spend a lot of time on this topology. I want you to kind of get used to the interface numbering scheme. Now back to some issues with spanning tree. Flooding is one of the things that drives us toward wanting and needing spanning tree in the first place. So let's think about what happens when C sends a frame. If we don't have spanning tree or rapid spanning tree, its newer and better cousin, The frame comes into switch 3 say forwards up to switch 1, and let's just say it's flooding the frame. It's a broadcast or an unknown unicast, and goes up to switch 1 is flooding, say it's a broadcast, so flooding's happening, goes to A, goes over to switch 2. Switch 2 forwards down and to the right. Switch 4 forwards left and to the right. And that's great. But notice this one that got forwarded to the left comes back to switch 3, and now we've started a loop. Because what's switch 3 going to do with the thing? It's going to flood it, right? So in fact, just to emphasize the point, if you take that frame again coming in from C and say it's a broadcast, it's getting flooded, that's what happened. You know, it goes around and it's going clockwise, and there you go. And the slide stopped, but the frame doesn't. It keeps getting flooded around and around. In fact, guess what? That original frame from C, when it comes in on the left, switch 3 forwards both here and here. So there's one going clockwise, and there's another frame going counterclockwise around this network. And neither stop. There's no time to live. There's no timeout. So you would, without spanning tree, flood your network this first moment that you got the first broadcast and bring it to its knees with pointless traffic. Yeah, that's bad. So not to overemphasize the point. We can't live like that, and that's why, many decades ago, over 40 years ago, I think now, so spanning tree was created to prevent that, to allow us to have redundancy and to take advantage of it, but not let these loops occur. So how does spanning tree do that? The end game is a spanning tree topology without redundancy, so there's no loop that could occur. There's no logical loop. And so what spanning tree would do, for instance, is say down here, quit using the link, or more accurately, quit using one interface, say switch 3's right-hand interface. And let's just say it did that. So C sends that frame, it's a broadcast, so switch 3 is going to forward up and around, but there when the frame comes back into switch 3, he won't process it. So its logic is, hey, I'm going to ignore any incoming frames on that port, and I'm not going to forward. I'm going to prevent any outgoing frames. While this orange arrow line shows that action, he never actually sends any frames there. Basically, it's disabling the port from forwarding and receiving, but a show interfaces command is going to show it's still in an up state. So it's kind of an overlaid state on that port, and we call that state blocking. So hence the word up in the title there. So that's a great thing. But we've got lots of details to get through in order to understand how and why spanning tree does that. So it's also bad to just not use redundant links. Like you might think, hey, well, instead of spanning tree, could we just, not use that link at the bottom at all? Not have it? Well, we want redundancy because things break, right? Somebody unplugs a cable, the cable goes bad, the switch loses power, but let's just say that top link has a problem. So before, when things are great, frames have a path to forward around, but when something happens with that orange Shazam up at the top there, that's no longer available. Well, it sure would be great if we had that physical link at the bottom. With spanning tree, it's logically disabled by spanning tree due to this blocking state. If that top link fails, then we remove the blocking state from the interface. That link goes down, and then we remove that blocking state, and frames can flow across that bottom link and reach the other devices in the network. All right, so that's a bit of context behind why we want spanning tree. Spanning tree wants to build a loop-free topology to overlay on the redundant physical topology. The first step to do that is that the switches get together and elect a root switch. How do they do that? Well, the rules are in the middle of this diagram. There's a thing called the bridge ID on each switch. It's a number, and the switch with the lowest number wins. All right? You can think of that number as two-part, priority and MAC address. So for instance, if you look at the priority values and think of them as hexadecimal numbers and say 8001 is a hex number in this case, these all happen to tie. So that'd be a tie on the priority. But if you looked at the full bridge ID, it'd be the juxtaposition of the priority and the MAC address here. And if you look at those four, the MAC address part's always going to be unique. It's a burned-in MAC address that's made unique by the switch manufacturer. So somebody's going to win then. That breaks the tie. And in this case, switch 1 has the lowest number in its bridge ID. It's got the lowest MAC address after the tie in the priority. So it becomes the root switch. Now, we don't have a loop-free topology yet. All we've got is step number 1 in getting there. Now, just a bit of trivia to point out here. Cisco switches, when you do show commands to look at spanning tree, they show the priority in decimal values and the MAC addresses in hexadecimal values. So that 8001 hex I showed on the previous page is the same as 32769 in decimal. And I'm not good at doing the conversion in my head that fast. I know it through repetition for 100 years. So that's the default priority you'd see in a Cisco switch in VLAN 1, as it turns out, 32769. So if you see that in your travels and studying for CCNA, that's why. That's default priority VLAN 1 Cisco switches. So all 4 switches, again, tie in priority in this case. And you do show commands, and you'll see that value. So again, they're going to choose the root switch based on the lowest bridge ID. In this case, tie on priority, lowest MAC address is switch SW1 again. But it doesn't have to be. It just is in this case in the drawing. You can reconfigure the priority values, and you'll learn to do that later on in your CCNA studies, not too far in the distant future. So if, again, I'm thinking in hexadecimal, just because I like thinking, since the MAC address is in hex, it's nice to think. The priority in hex, here's priority of 7001, 8001, 6001, 9001. Well, it doesn't matter what the MAC addresses are. In this case, this MAC address, this priority down here, 6001 is lowest. It's going to win no matter what the MAC addresses are. So switch 3 becomes the root switch in this particular case, based on configuration that might have been added. Now, I'm showing you the MAC addresses, but they don't matter. All right, at least to the root election. So that's a bit about the root election process. Before I go, just a bit about that idea of a base priority. You can only configure 16 different numbers for the priority in a Cisco switch. And those are the ones in this table. These are all multiples of 4096. It's just a bit of trivia. With spanning tree on a Cisco switch, there's a spanning tree for VLAN 1, a different one for VLAN 2, a different one for VLAN 3, and so on, per VLAN spanning tree. So the priority used, say if you've got the default base priority of 32,768, the actual priority in VLAN 1 is that plus 1, or 32,769. In VLAN 2, it's the base number plus 2. In VLAN 3, it's the base number plus 3, and so on. And that's how the switch creates a different priority value to use in each different VLAN for per VLAN spanning tree. All right, enough about this bridge ID and picking a root switch. Let's get into the next bit. This next bit is not complex, but it's detailed, so it can be a bit of a challenge. You're going to want to know this page, so you might want to note the time and come back and look at it again later. I'm going to talk about the first or top half of the page for a moment. There's one root switch. All the other switches are considered non-root switches as a description of those. So that one root switch is the one with the lowest bridge ID, so presumptively all the others are not the one with the lowest bridge ID. So it's important to note then on the non-root switches, they choose one of their ports. Each switch picks a port that's their root port. And that's important because a switch's root port forwards. That is, it does not block in this spanning tree protocol we're calculating. And we want to create this spanning tree topology, right? So we pick a root port on each non-root switch, and we calculate the root cost, and that's important to the underlying processes of how the switches do their work. So each non-root switch ends up calculating its root cost, which identifies its root port, and it forwards on the root port. That's the context. Let's talk examples. So to do all this, there's this idea of cost. Each port has a spanning tree protocol. Cost, by default, on a port that's running at 1 gigabit per second, it's running at 1 gig, the default cost is 4. All right? So those are the blue 4s that are scattered around beside each interface. So the first thing a non-root switch will do is calculate the possible cost from itself to the root switch and pick the lowest one. All right? So let's just say switch 1 is the root switch. So the other 3 are going to calculate the root cost over all the possible paths to reach the root. Now, One possible path is straight up here, say from switch 3 to the root is here, and the other is the long way around, right? So you'd think the long way around would have a higher cost, and it will in this case. But let's just talk through the process. So over this obviously short path, to calculate the cost, it's not the cost on both ends of the link. It's the cost from this non-root switch's perspective. It's the cost of any ports that are outgoing ports in this path. So frame would be forwarded out this port, come in switch 1's port. We only care about the cost on switch 3's port of 4. So the root cost over this path would be a total of 4. Now, there you go. There's your root cost. But let's consider the other direction just to make sure it's clear. It's the outgoing port cost from switch 3 all around the horn here. So what's that look like? 4 plus 4 plus 4 is 12. So there's the root cost of 12 that way. So switch S3 says, hey, that's great. So it's calculated two possible root cost values. One is 4, one is 12. Lower is better at layer 2. Just turns out the way they did different standards. So switch 3 is going to like this path here toward the root better. And that's how it determines its root port. It's the port that's part of the least cost path to reach the root. So if the root cost leaving this port 21 is 4 and the root cost leaving port 24 is 12, you guessed it, switch 3 is going to choose as its root port this port that ends in 21, and that port is going to forward in this new spanning tree topology that we're calculating. Whew! Sounds like a lot of work, but of course the switches do it very quickly and efficiently. But for us, it just takes a moment to learn what's going on. So I would hope that you would build skills then that you could analyze a topology and think, all right, well, what's the root cost over all the possible paths? What's the lowest one? And the port that begins that path is the root port on that switch. All right. We can affect this process by changing those cost values. They can be configured. So in this case, let's just say here down in switch 3, we reconfigured the cost from the default of 4 to something ridiculous like 20. And I made it ridiculous so that the other port would be chosen, as you might guess, just to make the point. So none of the other cost values have changed. Switch 1 is still the root switch. So in this case, if I consider the possible paths, I've got the same root cost 12 over the long way that goes through all the other switches. But now my direct path straight up to switch 1, that root cost is 20. So switch 3, when it says, hey, what's my least cost to reach the root? It's that cost 12, and it'll choose that right-hand port to be its root port. All right, so that's what we can do to affect some things. Now, you can also have ties. So let's go back to this set of default settings of cost 4 on each port. But now we're going to think about switch 4, which is opposite from switch 1, the root switch, in this topology. So as you might guess right away, we've got a root cost of 8 going over one path and a root cost of 8 going over the other path because it's just two outgoing interfaces of cost 4 in each case. So which one should switch 4 choose? Well, there are 3 tiebreakers. The first one breaks ties in modern networks, so you typically don't need to worry about the others. There are some cases where you go to the second and third tiebreaker, but most of the time you won't have to. But you should go back to that page and study it and understand it. Look at the book for those things too, for those of you that have it. But here's the first tiebreaker, all right? So switch 4 is faced with the dilemma of, hey, I can pick either because the root cost ties, but I really should have a consistent way to break the tie to make the process work. And the first tiebreaker is the lowest neighbor bridge ID. All right, so let's just say switch 2 has this bridge ID that begins in hex 7001, and switch 3 has one that begins in hex 8001. You guessed it, lower one up here. So switch 2 will be the neighbor with the better bridge ID. So switch 4 chooses the port that connects to switch 2 as its root port. All right, So we still haven't finished the process, but from a human sense, you should know now how the root switch is determined. So you could do that when analyzing a design. You should be able to figure out the root cost from each non-root switch's perspective and determine the root port from each non-root switch's perspective. So, more words, you're going to want to remember this point in the timeline as well. You should come back and study this. So on each link, there's one port that's the designated port. So on links between switches, switch to switch link, it's the port connected to the switch that has the lowest root cost. I'm going to show you examples of that. On links between a switch and a host, the host is not participating in spanning tree, so the switch always wins. All right, so if you see like access switches connected to host, the switch is always the designated port. Sometimes there'll be a tiebreaker. Two switches have the same root cost. So it's the same tiebreakers we had about choosing the root port, which is lowest neighbor bridge ID. Should solve that right off the bat. There are some cases where it breaks down to the second and third tiebreaker. You can memorize those. I'll leave that to you to figure out outside of this video. And then finally, once you've identified a designated port, you should also know that its state, that is what it does, is forwarding. So root ports forward, designated ports forward, and ports that are neither of those two, or neither a root port nor a designated port, they block. Their state is blocking. And that's how we create the spanning tree, or how spanning tree does it. We can understand it. All right, so let's do an example. So designated port on links to endpoints. So look at the endpoints on the outsides, left and right. The switches are the designated ports, DP for designated port. The PCs aren't participating in spanning tree. They have no concept of a root cost, so of course the switch is going to have the better, lower root cost. Now let's talk about the root itself. Root is a special case. The root is considered to have a cost 0 to itself. Its root cost is 0. So keep that in mind and think about this. On any links between the root and another switch, the root switch is going to have a lower cost. It's 0. All the other switches have a non-zero root cost. So there's our root switch. It's designated port on the link over to an endpoint. The root switch wins on every other link as well. Why is that? Its root cost is 0 and everybody else's is higher than 0. So you can get that out of the way right up front. Make all the root switches ports designated ports. Then go one by one on all the switch to switch links like we see here. What about the rest of those? Well, there's our root switch. It's got a root cost of 0. Here are the root costs of the other 3 if we're back to that scenario with all default port costs. All right. So with that calculation, it's pretty clear which switch wins the designated port election because it's based on the lowest root cost between the two switches on each link, right? So of course, the root switch always wins on its links. But how about this link between switches 3 and 4 and this link in between switches 2 and 4? Well, 4 loses in each case, right? So on the switch 2 to switch 4 link, switch 2 wins. On the switch 3 to switch 4 link, switch 3 wins. So those are the designated ports in this particular design. So the whole goal of this is coming up with a spanning tree protocol topology that's different from the physical topology. It's a subset that doesn't have redundancy in it, so loops don't occur. All right? So how do we determine that? Well, we go through all this process in order to create it, and in effect, in this case, we're going to take out that bottom link for now and only then use it again if something else breaks, right? So how do we do that? Well, we're going to block on that gig 1023 interface, but the reason is for the stuff we just talked about for the last, 20 minutes probably. So we have a root switch, turned out to be switch 1, and then each of the other switches chose a root port. Root port is a role. It's placed into the forwarding state, so it's part of the spanning tree protocol topology. Then we choose designated ports on each link. All the ports connected to endpoints become designated ports. They're part of the topology. They forward, so their role is designated port. The state is forwarding. And then on all the switch to switch links, we choose a designated port on either end of the link. The root switch always wins, and then on the other links, it's based on the lowest root cost. And now we're done placing roles for all the ports, and there's only one port left that doesn't have a role, and that's that switch 4 port on the left. So, because it has no role, it's given a blocking state. And that blocking state's the one that says, hey, if you would otherwise have wanted to forward frames out here, you don't. And if a frame happens to arrive in here, you ignore it. All right, so that's how we build our spanning tree protocol topology. All right, so I used a few words there. So there are port roles like root port, designated port. There's also disabled port, by the way, if a port's down or it's shut down, for instance. And then there's a corresponding port state. Spanning tree uses the words forwarding and blocking. By the way, rapid spanning tree, the faster, newer cousin that's only been out 20, 25 years, it uses the word discarding instead of blocking, by the way. All right, so you definitely want to remember those terms and names as well. So just to sum up for a moment, the process itself uses messages to do what I've described in more human terms, but the goal is to achieve this loop-free forwarding. So the root switch is elected based on the lowest bridge ID. The root port is chosen on non-root switches. So the root switch itself does not have a root port. So we calculate the root cost on each and every path, and then that switch picks a root port based on the least cost path. It's the port that's part of the least cost path. Then designated ports are chosen on each link based on the lowest root cost of the devices on that link. So switch to endpoint, the switch is always going to win, but on switch to switch links, it's the lowest root cost that wins the election. Well, thanks for hanging with me. Let me give you those promises as always. In the book, Volume 1, Chapter 9, the first section is Virtual LAN Concepts. More so than most, I would say read the whole section. Here's why. I go over a few more issues that drive the need for spanning tree. That's just good for real life, maybe for the exam. Also, the book takes a much more focused look at the mechanisms, how switches accomplish things with the messages, whereas I'm looking more to a human view of how to understand the result here in the video. Right. But there's no CLI that you need to go pick up. That happens in the next chapter, Chapter 10. All right, after that, I've got 2 review activities. They're both interviews. Say you walk into an interview, you see this drawing on the board, you might be asked, analyze spanning tree, tell me what happens, right? So, as always with these interviews, it's good if you do it. So that's way better than not doing it. But it's better if you'll give it a day or two, and best if you'll schedule it so you don't forget. And there's an associated video where I'll walk you through it. Do it first before you watch the video. That's my only suggestion. By the way, in this first interview, it's this topology with all default settings. So you already know the rules, right? Other than figuring out which switch will be root. Then for interview question number 2, same topology, but non-default settings to make you think a little bit differently. So you'll build some skills even with the first interview question, and hopefully you'll be able to exercise those in the second interview question. All right, final thing. I promised I'd give you something going forward or looking forward. Rapid spanning tree speeds up what happens when convergence happens. That is, something breaks or recovers. How do we figure out the new topology for spanning tree? So watch for the term alternate port in particular. It lets a switch have a port that's standing by ready to take over for the root port. It's very common. You'll see it in networks today. There's also a similar term called backup port. It's very rare today because it only happens when there's a hub, and you really don't find hubs out there in the wild very much at all. But backup ports are standing by to take over for a switch's designated port. Both have other conditions that have to be met for a port to be able to be an alternate port and a backup port. So that's the second section in Chapter 9 if you want to go look for a little more detail in the book, for instance. Thank you for hanging with me on this fairly long video. If this is your first time in the channel and you're thinking, oh my goodness, do I want to subscribe here? Please do. If you hung for this one, you're going to be great on the rest of them. So subscribe or click the bell. As always, give me a like or a comment or a share. It's always appreciated. Thanks for hanging out. Later.